Section 1.4 covers a variety of signal types that are used to model non-periodic or non-repeating signals. So any signal that we want to have a mathematical model of it that helps us with analysis and so on. So what we're going to do today is we're going to look at several of the building blocks of signals and do a little bit of analysis of them. And we're going to be using these signal types throughout the quarter and using more analysis tools on them. Remember, everything we're covering today is generally meant to be used as a building block to represent a more complete model of an overall real-world signal. So the first one we're going to look at is the unit step function. And the unit step is represented by a lowercase u, and it has a time argument. And it is the function that has value 0. And then at time 0, it has a discontinuity, and it jumps up to a value of 1. So this building block, we can apply transformations. So if I apply an amplitude and a time delay, I end up with a time delay of capital T seconds and an amplitude of A volts, whatever that is. So there's capital T and there's A. So now we can build these up further. For example, let's say that you are given this waveform. And let's say this happens at -4 seconds, -2 seconds, and 1 second. The signal goes up to 1 volt and goes down to -2 volts. And let's say we have some analysis tools, which we will develop later in the term, that we know how to use the analysis tools on unit steps. And now we want to apply it to a more complicated signal like this one. So the process is to build the signal out of unit steps. So let's call this signal here x of t. And if we start writing x of t, and focus on the first change the signal makes, we see it's 0 at negative time up till -4, just like the unit step is, and then it increases to 1 here at -4. So we can model that part by taking a unit step with amplitude 1, because that's what the red waveform is going up to. But now we're going to go at t minus the time delay, or the time that the signal comes on. And it comes on at -4, so it's t minus -4, or t plus 4. So when you see t plus 4, that means we're moving the waveform to the left. Now, if we just did that, we would have this signal right here. It would go on at 1 volt forever. So now what we need to do is we need to add a term to correct the signal for the change that it makes at time -2 here. So right here, everything is right. The red and the black signal are following each other until we get to -2. And then we see what happens. It decreases by 3 volts from 1 volt to -2 volts. And it does that at time -2. So we're going to subtract 3 times. So we're going to subtract 3 times a unit step. So that's going to cause the signal to, when you do a unit step, you have a sudden jump in voltage. So that's going to give us a sudden jump of -3 volts. So we can get from +1 to -2. And we want that to occur at -2 seconds. So the argument is going to be t minus -2 or t plus 2. And now we have the signal goes down here suddenly by 3 volts and then continues on forever. And we can make the next correction, and the final correction is going to be to go up 2 volts from negative 2 volts to 0 volts. So up 2 volts, and then we're going to multiply that by a unit step at time 1, so t minus 1. So there we go. We now have an expression for that original red waveform in terms of 3 unit steps. And like I said, the analysis tools that we're going to develop later in the class, we're going to be able to very easily do a lot of powerful analysis on an individual unit step that might be time shifted or have its amplitude changed. And when we have a system that's linear, we're going to talk about what that means in some more detail, but you'll remember discussion of linear systems from your circuits. When we have systems that are linear, we can apply superposition. So we can consider this 3 sources being summed up as functions of time, and then we can consider what the system, how it transforms each of them, and then we can add the results together. So we're going to cover more of why that is when we review linear systems in an upcoming section. But for now, that's how you would build the signal. One more thing about unit steps as a matter of introduction, and then we'll be using them for many things pretty soon. Now let's take a look at what happens when you have a time-reversed unit step. So let's go through a few transformations using properties that we recently covered. Let's start here. We'll do a few different axes. Let's start with a unit step with amplitude 5 volts delayed to be at 2 seconds. And then let's time reverse that. So if I time reverse it, I mirror it about the time axis, and I would come up with this here, 5 volts from negative infinity until negative 2 seconds, and then the voltage turns off. So in the top graph here, let's call this y1 of t, and the bottom graph y2 of t. y1 of t is going to be 5 times the unit step delayed to 2 seconds. Now, we can see by looking at the two graphs that y2 of t is y1 of negative t. So we take the expression for y1 right here, this expression for y1, and we replace all the t variables with negative t, and that's going to achieve our time reversal. So I have 5u of negative t minus 2. And that will give us the bottom graph. Now, notice here it's minus t minus 2, and the transition, the discontinuity, occurs at time negative 2. You are used to seeing, when you see a minus 2, you're used to saying, oh, you subtract the delay, so that would be at 2. But that's when you have time reversal, the sign also gets reversed there. So if you want to look at it this way, it might make a little more sense. I'm just factoring out the argument of the unit step there. And then we can say that that's my t plus 2. And the plus 2 is telling me that the transition happens at negative 2 in this case. And another way to check that you have it right is to make sure the transition is at the right point is I look at the graph and I say on this graph, the transition is happening when t is negative 2. So let me substitute in. The t variable is negative 2, so I get negative 2 plus 2. The argument here is 0. And yes, that's what I expect. The unit step function makes a transition when its argument is 0. So this bottom graph of y2, I have to write the unit step in one of these two ways. So that's how you get a signal that's on from negative infinity up until some finite time. Let's do another example and introduce a function that's related to the unit step. So this one is called the rectangle function. And the rectangle function is a duration of 1 second, 1 volt, or whatever your units are for the signal you're measuring, rectangular pulse centered at time is 0. So we can sketch that out. Here is a rectangular pulse scheduled at 0. It is 1 volt high, and because it has a width 1 and it's centered at time is 0, the transition here is happening at plus and minus 1/2. So there's a few different ways to write that out. Your book gives some different ones, but what one that we can do here, if we want, is we can write it out in terms of the unit step. So I have a function that turns on at minus 1/2. So u of t plus 1/2. And then I take a step down at positive 1/2. So minus u of t minus 1/2. So what I'm doing here is this part is giving me this edge, and this part is giving me this edge, and it's causing me to step up. So that is the rectangular function. It's convenient when I have a pulse that turns on and off, I can express it as one function. We can apply time scaling to this as well. So if I have t minus capital T delay over a duration factor, then what I've done is I've delayed the overall signal to have its center not at 0, but at capital T, and I have time scaled so that the duration will be tau. So if tau is a number like 3, then I'm going to be 3 seconds long. I'm dividing the argument by 3, so I'm slowing down time to stretch this from 1 second out to 3 seconds. So let's do an example for capital T is 5 and tau is 3. And if I draw the rectangular function for that, here at time is 5, I'm going to have the rectangular pulse. The duration is 3, so it goes from 3.5 to 6.5, and it has amplitude of 1. So that would be my rectangle at t minus 5 over 3. What about if I say I have a rectangle at, let's do t plus 2, but instead of divide by 3, instead of dividing by a number, let's multiply by a number. So now I can think of this as the denominator tau is 1/4. So I've shortened the duration to 1/4, I've sped up the function, and I have a transition at time is -2. So if I sketch that one out, so there's -1, -2, and I have a duration of 1/4. So I go 1/8 this way, and 1/8 to the left of -2, and then it's 0 outside of that range. So that's how the rectangle function can be used. So you can practice, there's a lot of good examples in the book and in the homework at the end of the chapter 1. You can practice representing more complicated signals by summing up unit steps and rectangles. Next one we want to look at is the ramp function. And this is called ramp function, R of t. And the ramp function instead of having a discontinuity in the value, it has a discontinuity only in the first derivatives, and it also turns out the higher derivatives. So the ramp function looks like this, and we have a couple different ways we could represent the ramp function. One thing that we could do is we could say the ramp function is defined as the integral of the unit step function. So it adds up the area in the unit step from negative infinity. And I can't have two t's here, so I better be careful. Let's use tau as the variable of integration from negative infinity up until t. So that's one way to look at the ramp function, is I've just taken a unit step. So let's just sketch a unit step here for reference. And what I'm doing with this integral is I'm saying integrate from negative infinity up to whatever the current time is. So I'm integrating this function from negative infinity, it's 0, and then up to some ending time. Maybe the ending time is negative, no area is accumulated. And once I get to positive times, then I just keep accumulating a constant area at 1 unit per second. So that's what I can do as an integral form. Another way to write the ramp function, and all of these are useful when you're solving different types of problems, so it's good to be familiar with them, is to say that the ramp function is equal to a piecewise linear function. And it has the value 0 some places, and it does that for values of t less than or equal to 0. And it has a straight ramp up, a first order line, first order polynomial with the value t when t is greater than or equal to 0. You'll notice here I have two different expressions that cover the case 0, but they don't disagree with each other. When t is 0, both of these are true. This is 0. So I see my limit from the left and my limit from the right are the same. There is no discontinuity in value in this function, unlike there was with the unit step. My limit from the left approaching 0 was 0. My limit from the right was 1. I had a discontinuity in value. So both of these forms can be useful in writing the ramp. One other way I'll show you is the ramp function. I can think of the straight line t as the building block, but then I want to zero it out before 0. So what function do we have that zeroes something out before 0 if I were to multiply it? This unit step right here. If I multiply by the unit step, I cause everything before 0 to be multiplied by 0 and removed, and everything after 0 to be multiplied by 1 and kept as it is. So this is another form for the ramp function. Each of these forms can be useful in different contexts. This third form, if you're doing a calculus problem, this one might be the most convenient to work with. If you're implementing in a programming language or you're trying to visualize something, thinking of the individual pieces and using this middle form would be most useful. And if you are applying linear systems theory, which we'll get to in chapter 2, this integral form that relates the two signals might be useful. So there's the ramp function. Now let's apply the ramp function to represent a signal that has a little more going on. Let's do this. Function starts off at 0, suddenly goes down to -2 volts, and it does that at -4 seconds, and then at -2 seconds, it starts a ramp up, and it does that until it crosses through 0 at 0, gets to 1 volt at 1 second, and then stays at 1 volt forever. So we have a signal that starts off at 0 volts, makes a few deviations, and then continues on. So let's call that y of t, and let's derive an expression for y of t using the ramp function and the step function that we have derived. So what we do is when we go through a problem like this, usually it's easiest to work from left to right. And in this case, the function starts off at 0, so it's very easy to do that. And we see the first value change in the function is at time -4. I have a step discontinuity. I have a discontinuity in value, but not in derivative. The value changes, but the derivative is still 0. So that tells me that I can use the unit step to do that. I am going to subtract the unit step. I go down 2 volts. And this occurs at time -4. So t plus 4 gives me time -4. So if I just did that, I would have this function. So now what I need to do is I need to add a term that gets the difference between the black function and the blue function. And what we can see now is there is a ramp, and it's going up with a slope, a 1-to-1 slope. It goes up 3 volts in 3 seconds. So that's just 1 times the ramp function. So just plus a ramp function. And when does it occur? It starts at -2, so t plus 2. And now that function would be following this, but now it departs from the black function at -2, and it goes up like this forever. So now the final correction we make is we have to bring this red function back down to the blue function. There is no sudden change in value at this breakpoint at time equals 1, but we see there is a linearly, gradually increasing difference. So the difference here in this red region that we need to correct for is itself a ramp, but it's going in the negative direction. So minus a ramp, and it's again has a 1-to-1 slope. I need to go down 1 volt every 1 second in order to flatten this out. And it is occurring at time 1, so t minus 1. So now between the ramp and the step function, we can approximate or exactly match any sketch of a function with linear segments by building up ramps and unit steps. So this is the first video on section 1.4 that covers the unit step and the ramp and the related functions. There is another video that covers the second half. So this is a large section. So when you're ready, please go on to the second video.